So this next lecture segment is about the mathematical laws that we need to know to answer certain questions in genetics. The first law is called the product law, or also called the multiplication rule. And you do need to memorize this because throughout genetics, in many different contexts, we will keep coming back to this law. The law reads, the probability that two independent events, event A and event B, will occur simultaneously is equal to the product of their separate probabilities. So it's written this way: probability of A and B equals probability of event A times probability of event B. For example, independent events would be two events that don't influence each other. So the probability that you would win the lottery is maybe 1 in a million on a good day. The probability that you'll be hit by lightning is probably even lower than that. Let's just say 1 in a million for that. So what's the probability that both events will happen to you simultaneously or at the same time? So the probability of event A and event B happening to the same person is equal to the probability of event A happening by itself times the probability of event B happening by itself. So the probability of getting hit by lightning and winning the lottery is equal to the probability of getting hit by lightning by itself times the probability of winning the lottery by itself. So in my example, 1 in a million times 1 in a million. That would be the probability that both things could happen to you at the same time. Your book uses dice to show you the same thing. If you roll one die twice, or you could even have two separate dice, the chance that you would get a 4 on the first die and a 4 on the second die is equal to the probability of getting a 4 on the first die times the probability of getting a 4 on the second die. So the probability of getting 2 4s equals the probability of getting 1 4 times the probability of getting 1 4 in separate rolls. If the probability of getting a 4 is 1 out of 6, then the probability of getting 2 4s is 1 out of 6 times 1 out of 6, which is 1 out of 36. Now, how do we apply this to a genetics problem? Let's say you have this question. What's the probability in a dihybrid cross of getting an offspring with a genotype big A, big A, big B, big B, big B, little b, excuse me? Well, the approach you want to take is having the genotype big A, and the genotype big B, little b are really independent events. So we can treat this dihybrid cross like two monohybrid crosses that are just occurring simultaneously. What do I mean by that? Well, I said it was a dihybrid cross. That means the parents are both big A, little a. So getting an offspring that's big A from two parents that are big A, little a is 1/4. The probability of getting an offspring that's big B, little b from two parents that are heterozygous for big B, little b is 1/2. And you can draw out the little Punnett squares that show these little monohybrid crosses of the big A, little a, and also the monohybrid cross of the big B, little b. And you can see where you're getting a 1/4 and a 1/2 numbers there. So the probability of both events of getting an offspring that is big A and big B, little b is simply the product of their individual probabilities, 1/4 times 1/2. So the probability of being big A, big B, little b in the dihybrid cross offspring is 1 out of 8. And I didn't have to draw the entire 4x4 grid in order to solve this. That's the beauty. So I say, if you don't believe me, you can draw that Punnett square out, but you'll believe me after that. So here's one that you don't want to have to draw out the Punnett square. I ask you this question: what's the probability of having an offspring that has this genotype, big A, big B, little b, big C, big D, little e, from two parents who are both heterozygous for all 5 genes? So we're doing a cross of this, cross to another one just like it. So this could be called the penta-hybrid cross. So in a penta-hybrid cross, what's the probability of getting an offspring that looks like this here? Nobody wants to draw out this Punnett square, so we want to solve it mathematically. Well, the answer is you're going to take each item by itself. You're going to say, okay, the probability of getting a big A offspring from two parents that are both big A, little a is 1/4. The probability of getting a big B, little b offspring from two parents that are big B, little b is 1/2. The probability of getting a big C, little c offspring from two parents that are big C, little c is 1/2. The probability of getting a big D offspring from two parents that are big D, little d is 1/4. And the probability of getting a little e offspring, from two parents that are big E, little e is 1/4. So we treat this like 5 separate monohybrid crosses for each letter, each gene type. And then we multiply up the probability of collectively having all of those results happen simultaneously. These results here that happen simultaneously is simply the product of all of these separate probabilities. So the probability of having this offspring from 2 pentahybrid parents is 1 out of 256. And we solve it without drawing some ginormous Punnett square. The only Punnett squares you might draw would be the small monohybrid type Punnett squares. So the multiplication law or the product law is important. You need to memorize it. The other law that's really pretty minor is called the sum law or the addition rule. Now this deals with events that are not independent, but rather events that we're going to call mutually exclusive. Independent events are 2 events that don't influence each other, and they can both happen at the same time. A mutually exclusive events cannot happen at the same time. So really mutually exclusive events would be 2 outcomes, 2 possible outcomes of the same event. Like flipping a coin, there's 2 outcomes, heads or tails. You can't get both of those in any one coin toss, because if you get one, it excludes the other, obviously. So mutually exclusive means if you get one event, it excludes the other event from happening at that time. All right, so 2 outcomes of one event would be mutually exclusive. So the probability that one or the other of 2 mutually exclusive events, A or B, is the sum of their separate probabilities. So the probability of one thing happening or another thing happening, A or B, equals the probability of event A happening plus the probability of event B happening. This would be, for example, it's something that we might see with a single roll of the die. If your question was, what's the probability that you would roll a 3 or a 4 on one roll, and you can't get both on a single roll, it's either going to be a 3 or a 4, or it could be a 1 or a 2 or a 5 or a 6. But you can't get both. So the probability of getting a 3 or a 4 is simply adding together the probability of getting a 3, 1 out of 6, plus the probability of getting a 4, 1 out of 6. And that reduces to 1/3. Okay, so what we're saying is the probability of getting a 3, like, well, let's say I told you you're in Vegas and I said, okay, if you roll a 3 or a 4, I'm going to give you $100. So you got your die. And so what's the chance that you're going to win the $100? Well, if you roll a 3 or a 4, either one is going to win you the $100. Because when I say or, that means I'll take either one. So that's why your chance of winning $100 is 1/3. Because you have a 1/6 chance of winning if you roll a 3, but you also have a 1/6 chance of winning if you roll a 4. So you really have 2 out of 6 chances to win, or 1/3. Okay, so when you see the word or, it means add the probabilities together. But this doesn't come up that much in genetics. It's actually, the addition rule is something that you almost do without thinking about it. For example, in a monohybrid cross, what's the probability of getting a big A offspring or a big A little a? Well, the probability of a big A is 1/4. The probability of a big A little a is 1/2. The probability of getting one or the other combined is 3/4. So you almost do that already in your head without thinking about the actual law.